So the first law of thermodynamics, as we recall, says that energy as conserved, or the total energy of the universe, is constant, or the change in the universe equals the change of our system plus the change of the surroundings, and those together equals 0. So we're going to be looking specifically at changes of energy today, changes of enthalpy, and what we can do with these state functions as far as calculations. So pretty interesting things about thermodynamics. Also recall that we can rearrange the equation of delta E. It equals delta H minus PV work. And so when we do this and we have constant pressure, the bottom line, and I won't go through the derivation here, but that the change in enthalpy of a reaction equals the heat at constant pressure, because the work in the delta E and this negative work cancel out. And so at constant pressure, like we'll be doing all of our experiments today, the pressure of the atmosphere in our fake laboratory, the Q that we generate will be the delta H that we calculate. So there's some nomenclature we need to make sure that we're aware of. So we can have an enthalpy that's positive or negative. If our initial energetic state is higher than our final energetic state, i.e. we are decreasing our energy, then we're going to be releasing heat to the surroundings. And so the enthalpy of our products has to be less than the enthalpy of our reactants. So the delta H is negative, it's less than 0. And of course, the other side of that is that if our initial state is lower than our final state, then that heat will have to be absorbed from the surroundings. And so then the delta H will be positive, and it will be an endothermic reaction. So how do we measure this energy change? Well, so we understand that the heat released or absorbed, if it's endothermic or exothermic, is generally related to temperature. We almost think about these things intuitively as the same for a long time before we take a chemistry class. But the magnitude of how much the temperature changes depends on something called the heat capacity. The heat capacity of an object, C, is the amount of energy, Q, the amount of heat it takes to change the temperature 1 degree C or 1 Kelvin. And recall, this is a delta T, so it's the change in temperature, and because Celsius and Kelvin, they scale exactly linearly, they're just shifted by 273 Celsius, that the change in Celsius and the change in Kelvin are the same number. So if I say Kelvin here, it's because that's the SI unit that should be used here, but our measurements tonight will be in Celsius, and when you do a delta T in Celsius, it's going to be the same as the delta T in Kelvin. So that's an object that's just given, like a cup, the heat capacity of an object. But for a substance, we need the specific heat capacity, and this is what we're going to be using a lot tonight. And so this is the specific amount of heat that's required to change 1 gram of a certain substance, 1 degree C or 1 Kelvin, the amount of energy that it takes. So this is a constant of every material. So where do we encounter this? Well, imagine that you're in a room somewhere, and that room has a wooden door with a metal knob. Now, everything in that room is the same temperature. The temperature is given by the energy in the molecules of the air, and it's affecting all surfaces evenly. So that door with the metal knob, both of the door and the knob are the same temperature, but they have drastically different heat capacities. The heat capacity of a metal is much smaller than the heat capacity of the wood, and therefore it takes a lot less energy to change temperature, the metal does, than the wood. And that's why when we touch the wooden door versus touching the metal knob feels colder than the door, but they're the same temperature. What's the difference? Is how much energy is transferred as temperature changes. And so the metal lower heat capacity or specific heat capacity is what gives rise to this feeling as it's drawing more heat from your body than the wood is. And so recall that we can then calculate with this heat capacity, this specific heat capacity, the heat that's transferred by some material if we know the mass of that material and the change in temperature, which is either C or K, because it would be the same value. So the instrument that we're going to be using tonight and that most experimentalists use for this when you're doing constant pressure calorimetry, and you'll have to look in your book about bomb calorimetry because we're not going to be covering that tonight, but that would be a different form of calorimetry. What we're going to have is actually 2 seated coffee cups work so well for this experiment that there isn't much purpose in the regular lab to use anything but this. So every institution that I've ever worked for or learned at has had this kind of experiment and just 2 styrofoam coffee cups. Because what happens is that if we recall the first law of thermodynamics, it says that we have to conserve our energy, which means that the energy that's given off has to be the energy that's taken up. And so we're going to see that in that if we put 2 objects in our calorimeter, none of that energy is going to get out of the calorimeter, or that's going to be the assumption that we're going to use, which means whatever heat was taken up by the cold, so remember it's absorbed here because we have a positive sign, has to be given off by the heat of whatever is hot. So that's a negative sign. So in this example, we have a piece of metal that's hot and it's giving off the heat, and that heat would then be absorbed by the water and also a little bit by the calorimeter itself. And so this is what that math would look like, no matter what the object that is giving off heat, whether it was water itself or a piece of metal, this is how we would set it up. And what this says here is that this is Q of the cold water, the mass of the cold, the heat capacity of the cold, and the change of the cold, plus this is the heat capacity, not the specific heat capacity now, but just the heat capacity of the calorimeter. The calorimeter will absorb some heat, but not based on mass, it's just a calorimeter. So here the units are just joules per Kelvin or joules per degree C, and we multiply that by how much the delta T of cold is, and we'll get exactly the difference between delta T cold and delta T hot. And all of that energy that's taken up because of the first law of thermodynamics has to be the same amount of energy given off by the hot metal or the hot water. So we can take the mass of that, this is equal to Q as well, the mass of the hot water times the specific heat capacity of the hot water times the delta T of the hot water. And we want to make sure it is so important that we track our signs and that the signs are relevant. What is giving off heat tonight and what is taking up heat? In every step of this experiment, not being able to fully track those signs is going to be devastating for the math. So make sure that you're aware of where that sign is. But giving off, exothermically giving off heat should have a negative sign. So the first thing that we want to do is we want to find what is this calorimeter constant. Any one of these experiments, we need to know for our specific cups, and this is different for every different seated cups, how much heat will our cup take up for every change in temperature. And so we normally do this by just adding cold water and hot water to our calorimeter. So we're going to add 50 mils, or we'll use the density. And this is an example, and then I'm going to show you exactly what it looks like in the lab. But this is just a generic example. So we're going to add 50 grams or 50 mils. We'll say 1 gram per mil, the density of water tonight throughout these experiments. So we have the mass of the cold water, and we know its initial temperature, 10 degrees C. So we'll get to that in a second. So we have some information about delta T cold. And then we're going to add at the same time the mass of 50 mils, 50 grams of water. That's 90 degrees C. We're going to mix those at the same time. And then at the end, we have 100 mils of water. That's 44.2 degrees C. So this would be our final temperature. So graphically, don't have to do a graph tonight. So I did one for you, so don't worry about that. But I just wanted to show you another way to think of this, is if we were tracking over time the temperature of our 2 solutions, we'd have this hot solution that's staying 90 degrees C, and our 50 grams of cold solution. And then at some time, we're going to mix them, and then we'll have one solution at a new temperature. And so if we think about these delta T's, the delta T hot, delta T is always going to be final minus initial, but there's a perspective here now when we have 2 different materials, one that's giving off heat, one that's picking up heat. So from the perspective of the hot water that we're adding, this red water, it's T final minus T hot. It initially was hot and it became this final temperature. And for delta T cold, it's final minus initial, but now this cold water originally was a cold temperature and it heated up. And so the delta T cold is T final minus T cold. And so now we can take these delta T's and these masses and we can plug all of them in, and keep in mind the calorimeter is not giving off heat to the solution, it's taking up heat. So it's always going to be on the side of the taking up, the positive sign of Q, not the negative sign of Q, which is giving off heat. And so then the only thing left is this CS and this C cal. And so we're going to plug in the specific heat capacity of water. And all of our solutions tonight, even our hydrochloric acid and our salt solutions, which we'll get to, they're all going to be mostly water. And while it's not a perfect assumption for tonight, all of our solutions will have the specific heat capacity of water. And it's a good one. And if it's different, it's going to be very slightly different. And for our math and for this experiment tonight, let's just keep it simple and say that the specific heat capacity of our water and our solutions will always be 4.184 joules per gram Kelvin, or gram degree C. And so when we plug that in here for the heat capacity, then we have mass, delta T cold, mass of hot, delta T hot, and the CS, the specific heat capacity of water. And we're then allowed to solve for the calorimeter constant. And this will be the first thing that we need to do today. So we're going to jump in like we normally do. And you all know now, you're experts on how to set this up, so I won't belabor it, but make sure you read that background information. There's a lot of important information there. If this feels fast, there's it's going to be reiterated there. So I'm going to kind of walk you through getting the heat capacity of the calorimeter. I'm not going to give you that final temperature, so you can't just do it all here with what I'm showing you. But what I am going to show you is that these symbols will color as we find the data. So I want to show you where we're going to find the data in this experiment, in this first set of determining the calorimeter constant, and where in the math it's going to go, because we're going to collect a lot of data, but we have to know where to plug it in and how to use it. So we're going to start with a hot water bath. This is going to be our hot sample. So we'll do the same thing that I just demonstrated, hot water and cold water in our calorimeter. So we're going to zero the balance like we did last week and add 45 mils or 45 grams of DI water. The system will ask you in volume, but you'll see then that there is 45 grams. The density is going to be 1 today. So you'll have 45 grams of your mass of your hot solution, and you'll put it in your hot water bath. This is going to take a little bit of time. In our real time, it takes a little bit of time for this to heat up. So as you see my slides progress, you're going to see that the temperature is not exactly 60. It would not be appropriate to mix these and get your final temperature until it was exactly at 60. Remember, in that graph that I made, those temperature dots were straight. They were constant. That was my assumption for that example. But we need to make sure that we have a very good idea of what T hot is, not just the bath that it's sitting in. So make sure that you do that. See, 51.7, we're not there yet. But while it's heating up, we can get going with our calorimeter. The calorimeter, again, just styrofoam cups. So we'll put them and we'll zero our balance out. And then to this will be our cold water. And so we'll just add 45 grams or 45 mils. And so that's going to be the mass of our cold. And so we have our delta T hot. It's almost at 60. So we're cruising right along, and we need a thermometer for each. And this delta of this 21.5 C, that's our virtual lab temperature. That is going to be our T cold. So now we have our masses of our cold hot and our T hot and our T cold. And so now we're just looking for this this T final. And so you're just going to transfer, drag and drop your solution, your hot solution, into the cold calorimeter. You don't want to go the other direction. The calorimeter is insulated, and we have this massive assumption that we lose no energy to the surroundings. That is critical assumption in what we're doing today. So if we put it in glass, it's going to drastically lose its heat to the surroundings. It's not going to work the way that we expect it to. So make sure that you're working within that calorimeter, because it could seem a little bit like you could do it either way. And of course, you're just going to pour all. And so I've used a little bit of a sensor here. But so this you would read as a T final. And you can expect that it's going to be lower than 60 and higher than the initial temperature of the cold water, which was 21.5. So you should expect something like that. The calorimeter, the assumption that there's heat is never lost is not always, is never actually true. There's little bits of air and space in which the heat will get out. So you're going to want to make sure that you're really quick on making sure that you capture that T final, because if you don't and you let it kind of slowly go down, then your math isn't going to work out the same. So the T final, you should see it as soon as the temperatures mix, it should go from the cold temperature, which in this case is 21.5, up to some higher number, and then you want to write that down. And then, so then we're looking for this C-cal. And so if we have the specific heat capacity of water, which is 4.184 joules per Kelvin gram, we can plug that in here and here. And now we see we've redded all of our elements here. We've collected everything from our data. and we can solve then for the calorimeter constant. Sophia, did you have a question? I saw your hand raised.
Yeah, so I haven't gone to these lectures. Are we supposed to just be like observing or listening to you? We're not supposed to be writing down any of this.
Yeah, you might wanna write some of this down. I think that specifically the equations, I would write down the equations as you're going.
But not like 45 grams, because like we're gonna be doing
No, that's
that.
going to be in the procedure. That's going to be in the procedure. I'm
Okay,
trying to tie in what it's going to look like for you to do the lab with where the data goes in the analysis. So the procedure will be there and you don't have to write the procedure down. That's a very good question.
Okay.
What I've been trying to do with this lecture is try to get you to see what the procedure looks like and hopefully understand, without giving you all of the information, what to do with that data so that we're not just stuck at home, because some people do these labs asynchronously and can get a little bit trapped. So that's what we're doing here. We're going to solve for the calorimeter constant. That's going to be important because we're going to use the same calorimeter for the rest of our experiments. We're actually looking at enthalpy now, but it's always going to be absorbing some energy based on how much the temperature changes from cold to final. And so we need to account for that in our math. Otherwise, our math will always be off. All of our numbers will be off. So just make sure you understand we're always going to be using this calorimeter constant, but we'll only solve for it this first time.
I have a quick question.
Sure,
About the
go
other
ahead.
slide.
Oh yeah, go ahead.
Okay, when you're taking the temperature of the hot,
Yeah.
is it the one inside the Erlenmeyer flask?
Yeah,
Or
it's 60. Mm-hmm.
okay, so then once we put it into the cup, it's when we take the final?
Yes. So whatever's reading here in this red box, I just covered it up, because if I gave it to you, then I've done the entire lab and all of the data points, and I can't really fudge it. So I'm saying that this is where you would get T final after you've done this pour all. So you've added them, you say pour all, and then the T final will appear in the coffee cup calorimeter.
Okay, and the same thing would be for the cold water, right? First, we look at the Erlenmeyer flask, and then once we put it in, or would we be adding the cold water into the hot water?
Yeah, so we're technically adding the hot to the cold. This is a really good question, and it's why I'm really belaboring this, but I want to bring you back to this. There's 3 temperatures that you're looking for in this experiment, and the rest of them, then there'll only be 2, and it'll be slightly less confusing. But in this one, you're going to have an initial hot and an initial cold. You're going to mix those and get a final temperature. They're going to be somewhere in between those two. So in this case, we had 90 and we had 10, and then our final temperature was 44.2. Why was it not 45? Why was it not or 40, exactly in the middle? Well, because of this calorimeter constant. Some of the energy was taken up by the calorimeter. So,
okay, so our final is once we mix both of them.
Right, exactly, yes.
Okay,
yes.
I was confusing that. I thought you were first doing the cold and then the hot, but it's once you mix them together.
Right, so that's the hot, and then we've added the cold. And so this is the cold temperature, 21.5, and the hot temperature will be 60. We're gonna let it completely heat up. So that'll be T hot, T cold, and then we'll mix them, and then we're mixing it into the calorimeter. And so then this will read T final, and it should be greater than T cold, but less than T hot, which is what we would expect.
Okay, okay.
Great question. No, I'm really glad that these questions are being asked, because this is a little bit tricky. I don't think it's hard, and that's what's great. It's not going to be a hard experiment, but if we're totally going to it blind, we could get a little bit twisted here. Okay, and that's what we're solving.
Hey, I have another question. Sorry.
Sure, go ahead. No.
So I was doing the pre-lab last night or this morning, whichever one it is, and the very last part of it that involved the calorimeter and the water, I basically, I think it was just transferred into the calorimeter, and I was supposed to weigh it. Actually, so I just remembered I have 2 kind of questions. The first one is the temperature that is, I think, gradually increasing, that I have to write down right after the reaction completes. According to what I observed, the reaction took a really long time, and I just stopped it in the middle of the thing, and I wasn't sure if what it showed right after it, like the the liquid was put into the colorimeter was placed in there, like was the temperature right after that showed or after the reaction was apparently going. And so that was a little bit confusing as to which one I would put down, because otherwise I would have to like wait maybe a half hour before it would stop like increasing.
Whoa.
So that's the first question.
Okay. Okay, so the answer to that is that if the temperature is, if it's an exothermic reaction, so that I think that you're specifically talking about what we're about to do next, where it's not just get a calorimeter constant, which is a little bit more straightforward, and some of the things that you said, I think, come from the enthalpy of a reaction. So if it's an exothermic reaction, then the temperature will increase when we mix them, and then it will stop increasing at a certain point, and then it will begin decreasing. And so we're going to be looking for the point at which it goes from increasing to decreasing. And that last point up, that would be the highest point. So I'm not sure if this, how much the simulation makes you wait. It didn't seem to me like it made you wait very much. But when you actually do these enthalpy of reaction in a coffee cup calorimeter, you're right, there's some mixing time, and then the heat will, if it's an exothermic reaction, will rise, and you'll watch your thermostat. And so it's really, really important that you're really, once you mix those, your eyes are fixed on the thermometer so that you're really able to see what's happening. If it's an endothermic reaction, then it's going to decrease in temperature once you start the reaction. And then at some point, then it's below room temperature. And so at some point, it's going to start taking heat in from the room because it isn't a perfect calorimeter, and the heat will start going back up. So in that case, in an endothermic reaction, you're going to be looking for that lowest point where before it started going up, and that would be your final temperature. And again, I'm pretty sure that it's pretty quick in this experiment today. The computer is pretty generous. It does have some temperature delays. We've seen that. We just saw that in heating up the water. But it's a minute. It should not be 30 minutes. And if it is 30 minutes, you should definitely talk to me, and I'll take a look.
So we're supposed to have had the pre-lab done already, or is that to be done?
It should be done, but we can talk about it and work through any little problems that might have come up, okay?
Okay.
Was there a second question?
Yeah, well, I think it was basically around the same area as what I had asked before. Basically, I think it was like the next step, but we were supposed to like measure the mass of the water in the calorimeter on the balance, and I noticed that it didn't say anything about taking the thermometer out, so I put them both on it, and then when I took it off, it changed the mass, and I knew there was like 25 grams, I think, of water, and it said that with both of them on.
Yeah.
So I was like, am I supposed to figure it out because it's them combined and I subtract the mass, or count for both of them?
Yeah, let me show you right now, okay? So this is the reaction that is in question, the one that we're talking about. So you're gonna add magnesium solid into hydrochloric acid at a 1 to 2 mole ratio. You're gonna yield magnesium chloride and produce H2 gas. Now, we're gonna add some known mass of HCl and some known mass of magnesium solid. But if you look at this reaction, we're going to be losing some of our mass of hydrogen in form of gas. And so we need to account for that so that we can get the mass of the solution. What is the mass of the solution? And so as Alexander was talking about, we have to get an initial mass of our calorimeter, and we have to get our final mass with the solution in it, and weigh by difference to determine what the actual mass of the solution, so that we can do our MCAT and solve for delta H. So I'll show you exactly where we're going to get that. But here now in a queue of a reaction, the way that we want to think about this, and we're going to be doing reaction enthalpy for the rest of the day. So it's just going to be a one-sided MCAT situation, because the reaction is going to either be giving off or taking up energy. And we're going to be measuring the solution and what's happening there. And it's very, very important that we all understand that whatever the reaction is doing, the solution is doing the opposite of that. If the solution is heating up, that's because the reaction is giving off heat. And if the solution is cooling down, it's because the reaction is drawing in heat. And so make sure that you have a good grasp on the fact that when we're solving for the Q of reaction, which we will at the end, we're going to take all of our data, and then we're going to need to flip the sign, because this would be the Q of solution, and this would be the Q of reaction, and they have opposite signs. What happens to one is the opposite of what's happening to the other. So we're measuring the Q of the solution, And so it's important to recall that there's this element here, C cal, which we just solved for, times whatever the delta T is, plus mass of the solution, which Alexander and I were just discussing is necessary. CS, that's the specific heat capacity tonight, we'll just say of water, which is in your, all the information is 4.184 joules per gram Kelvin, and then of course that same delta T. So there's only one delta T here. There'll be an initial temperature of our solution before the reaction and a final temperature, final minus initial. It'll be really easy going forward from here to find that data.
I have a quick question.
Sure, what's up?
I just caught this. Going back to measuring the water, I see that we have the mass of cold water and the mass of hot water.
Right.
Would those be the same, or would they be?
They are going to be the same because we added the same amount of water. We have to account for that because the water has a specific heat capacity. For every gram of water, it can take in more or less energy. But you could absolutely do this with a different amount. You could have 50 grams of hot water and 76 grams of cold water, and you could mix them and get a final temperature, and you could back calculate the same calorimeter constant. But that's just confusing. And so for the most part, this experiment has 40. My example that I made some other time had, this one has 45, that one had 50. It really doesn't matter. It's based on your experimental setup. They don't have to be the same. And so that's an important thing to account for, because if they are different, you would want to make sure you have the correct masses over there. Good question.
Okay, and so for this one, we'd have to use the mass of the element, right?
This is going to be the actual mass of water that you put in. So 45 grams of water, hot water, and 45 grams of cold water that you've added.
Oh, okay.
So to solve, So to solve for the enthalpy of the reaction, then we can take that Q of the reaction, and then we have to find the moles. But unfortunately, we don't know exactly what the limiting reagent is. And so one of these won't be completely converted into magnesium chloride. So you need to find out what the limiting reagent is. And to solve for the delta H of the reaction today, you want to solve for the Q of the reaction, which is the opposite of all of this stuff that's happening to the solution, and then divide by the moles of the limiting reagent. So that's not going to be the stoichiometric number. It's not going to be 1 or 2 unless you calculate the moles, and I'll show you exactly where we get these from, of 1 or 2. This is the actual amount of moles that you have produced or that you have consumed. It is how much energy is given off when this reaction goes. But if we don't add 1 entire mole of magnesium, for instance, then we're not going to generate 1 mole's worth of enthalpy. And so to solve for what it is in any number of moles, we divide by the moles tonight of the limiting reagent. And I'll make it clear for every step on what the moles are that you'll be looking for to divide by. And then recall, we'll be using that specific heat capacity of water and that calorimeter constant that we found from part 1. And we can solve for the Q of this reaction. We're going to be doing this now. I'm going to show you how to do it. And then we're going to be doing it for the rest of the night. It'll just be this kind of calorimeter cup reaction measurement, and then dividing by some moles to find the delta H. And so for the first experiment, we're just going to be finding out the enthalpy of the reaction. So I'm going to show you what the data that is being collected, and it's going to collect over here. And then after I show you collecting it, I'll show you where to put it in. But so we'll need a calorimeter. We're going to need one for the rest of the night. We're going to get a mass, an initial mass of our calorimeter. And so this was what Alexander was alluding to. We need to know what the mass of the solution is afterwards. And so make a note. I don't have the thermometer here when I get the initial weight. So when I get the final weight, the only thing that can be different is the solution inside. So we have to make sure that even if the instructions don't say, take out your thermometer before you get the final mass. But so now we've got our initial calorimeter mass, and we need to record that. We can zero it out, as the instructions say, and then add 0.150 grams of magnesium. And we can see then our balance says that we have 0.150 grams of magnesium. So we can have now our mass of magnesium that we're starting with, and we can, of course, convert that to moles of magnesium, which we'll need for the limiting reagent determination. And so then we can move that off the balance and add a thermometer and get an initial temperature, which will always be 21.5 in our room. And then we need to add our HCl to complete our reaction. So we're going to use 1 molar hydrochloric acid and add 45 mils. And so if we have the volume, 45 mils or 0.045 liters, and the molarity, 1 mole per liter, then of HCl, then we know the moles of HCl. So we'll need that again for the limiting reagent determination. And you can double click and make sure that your volume is correct. And then you want to transfer it. You want to start your reaction. So you're just going to drag the HCl over your calorimeter and transfer all. And you'll see a T final appear, and you record that final temperature. After you get your final temperature and you're satisfied with it, you will then return the thermometer to the shelf. You'll let your calorimeter cool until it's room temp, and you can place it on the balance. And you can get a final calorimeter mass, and then you can subtract those to get the mass of the solution. So we're going to do this 3 times, and let me show you exactly what we're going to do with the data that I just collected here. And then once you're done, then you'll go, instead of 0.150 grams, you'll do 0.250 and 0.350 grams of magnesium respectively. So you'll do 3 runs of this experiment. So here's our data that we've collected and our reaction scheme. We're solving for our enthalpy. So our Q of our reaction, the first thing is the mass of the solution. Here will be the final calorimeter mass minus the initial calorimeter mass, and make sure there's no thermometer in there. And that's where we get this, the mass of the solution. The delta T is that final temperature that I just censored, minus that initial temperature, which would be 21.5 Celsius. And that'll give us our delta T, and it'll be used for both of these. We're going from cold to hot or hot to cold, but it's just one direction, so just 1 delta T here. And then we're going to plug in the heat capacity of water and the calorimeter constant, and so we have all of our data then. And so finally, then we're solving for Q. So we plug all this data in, we get a number, we flip the sign to get Q of reaction, and then we take that number and we divide it by those moles of limiting reagent. So finding the moles of magnesium using molar mass, the mass and the molar mass of magnesium from our periodic table, and moles of HCl found with the volume of HCl and the molarity of the solution. And then this balanced chemical equation here, and using stoichiometry, we can determine what the limiting reagent is, what's going to run out first. So the next thing, so that's how we're going to determine delta H of our reaction. So then we're pretty much just done with part 2. And part 3, why I call it, which is about Hess's law, is really the 2 last parts, parts 3 and 4. But I'm going to kind of sew it all together in one explanation. And I'm not going to show you any more of how to collect the data, because the data will be collected exactly the same way. I'll go over what data you collected, more importantly, what you do with it. But you're going to just be doing the reactions very simply the way in the coffee cup calorimeter, getting those temperatures, getting that mass of the solution, using that calorimeter constant, flipping that sign, dividing by moles, and getting delta H several more times.
I have a quick question.
Sure.
I just want to make sure the moles of the limiting reagent are the limiting reactant that we get from magnesium. Yeah. And okay.
Limiting reactant. I'm sorry. You can think of those interchangeably.
Okay.
You can have it as reagent and reactant. So.
Okay.
Wait, I got a quick question. Why do you have to add the specific heat constant times the change in temperature? So like that left side of the
this one here?
Yeah. Why do you have to like add that one?
Great question, Abe. So that's the calorimeter constant. That's how much energy that it takes for the calorimeter to change temperature. And so the calorimeter as styrofoam is going to absorb some energy as well as the solution. So in that first step, we figured out the calorimeter constant, the joules per change in Kelvin, that the calorimeter will always take up. And so if the reaction is giving off heat or taking up heat, then we're going to have some interaction with the calorimeter as well as the solution. So this is accounting for the presence and the physical interaction of the material that is the calorimeter. But we don't have to worry about mass because it's the same calorimeter every time. It's just the heat capacity, not the specific heat capacity of the calorimeter.
Okay. Got it. Thank you.
Sure, yeah. So Hess's law that we're going to be using tonight to use some of these enthalpies that we derive. So now we feel, okay, we kind of understand Q, kind of understand delta H. Hess's law is like one step further. Now we're going to take some more delta H's that you're going to measure and calculate, and then we're going to use Hess's law to find the delta H of a completely different reaction that we can't do even in this digital lab. And that's because the internal energy and delta H are something called a state function, which simply means that it doesn't matter the starting and the final place, or all it matters, excuse me, is the starting and final place. It's path independent. The only thing is that final minus initial is the change in the thing, and that's what a state function is. So if we use my little pictorial example, try not to belabor it, I just think I have way too much fun with this. If our initial location is our house and our final destination is our school, and this was a state function, you can understand that there's many different ways to drive from the same home on different days, depending on traffic or whatnot, to get to school. And on a different day, you might take off, miss a turn, have to reroute, and Siri takes you on a bad route. So now if this was a state function, we would say that the delta is final minus initial, and it would be the same even though these paths are different. So the distance between school and home, the delta distance, is the same in both cases. You are the same distance from your home. It's just that you took a different route. And if we know that as some truth about certain functions, these state functions, we can manipulate some of these truths to find out something which otherwise we couldn't. And that's Hess's law. So delta H, delta E, delta T, delta P, delta V are state functions. Path independent, they depend only on those initial and final states. So some chemical process are too complex to occur in a single step or series of reactions. And so we can use something called Hess's law. And Hess's law says because delta H is a state function, then the overall enthalpy change of a reaction, if you know steps of what it takes to get to that reaction, whether they are actual steps of the reaction or just even theoretical steps that mathematically work, if you add up all those enthalpies, you'll get the enthalpy of the overall reaction. You can also use Hess's law if you don't know delta H1, but you know delta H of the overall reaction, and you know all but one step enthalpy. You can, of course, reverse calculate for that enthalpy, that delta H1. But tonight, we're going to be just using a straight Hess's law analysis to find the enthalpy of an overall reaction by taking some smaller reactions and adding up those enthalpies in the correct way. But it's not quite that simple, because we have to make sure that our enthalpies have the right sign and the right magnitude. So the way to use Hess's law, this overall enthalpy, change in overall enthalpy, is the sum of all the changes of their steps, is the first thing you have to do is identify a target equation. What is the equation, the overall reaction, that you want to generate, but for some reason you can't? So you have to know that before you can begin. Then you need to figure out what reactions, and we'll tell you tonight, what reactions you have to find the delta H1, the delta H2, the delta change in enthalpy for all of the reactions that you want to add up. And you want to then make sure that the products and reactants that are going to cancel or stay are in the right locations. If it's supposed to end as a reactant, it needs to end as a reactant. If it needs to start as a product, it needs to start as a product. How we adjust those reactions is that if we flip a reaction, and I'll show this to you in a second, we're going to flip the sign of delta H. If we need to adjust for the number of moles, and I don't think we're going to be doing this tonight, but absolutely it's going to be coming up on the final. So if you adjust the number of moles of one of these intermediate reactions, you will need to scale delta H by that same factor. So if you multiply by 2, you have to multiply delta H by 2. So we adjust the reactions in two ways. We flip the sign if we flip the reaction. We multiply by the same factor if we need to multiply the moles. And then finally, then we just add up those equations, hopefully that things are canceling out if Hess's law is going to work. And when we cancel everything out, we end up with our target equation. And then we add up the delta H's, keeping all of the change in signs and all of the multiplied factors. But once we add up those numbers, then we should get the target equations delta H. And so with all that said, what does this mean for us tonight? So here's our target reaction. It's this ammonium chloride solid being heated up and forming ammonia gas and hydrogen chloride gas. And we don't know the delta H of this overall reaction. And we can't do this in our coffee cup calorimeter because it requires a temperature of at least 340 degrees C to start to see this decombustion. And so we can't do that and put that in water. It's going to melt the styrofoam, even if it's a simulate styrofoam. So this would be a Hess's law setup. How can we figure out what the enthalpy of this reaction is? So we're going to do 2 reactions in our simulate lab. We're going to be doing them in the exact same way we did that part 2 enthalpy calculation. So we're going to, the first one is a neutralization reaction of hydrochloric acid and ammonia aqueous, and we're going to make ammonium chloride aqueous, and we're going to solve for a delta H. We're going to do that in the same way. We're going to have moles, we're going to have initial temperature, we're going to have moles of HCl, we're going to have a final temperature, and we're going to have our total solution volume, which is our solution mass, and that will have a density of 1 gram per mil. So we'll get our solution mass by the 2 volumes of solution that we added and this density of 1. So that's all of the data that we're going to need to collect: the mass of solution, the heat capacity of the solution is the same as water, the delta T's is the final minus initial, and the calorimeter constant from part 1. We'll flip that sign to get the Q of reaction. The delta H of reaction then is the Q of the reaction divided by the moles produced of ammonium chloride. Just use the moles produced. It's all 1 to 1 to 1 here, so it really doesn't matter. Use this and you can get the delta H of delta H1. We're going to do 2 of these ladder reactions, and the second one is going to be the dissolving of ammonium chloride solid in solution to make ammonium chloride aqueous. And so we're going to be measuring the mass. So in this case, the mass of the solution is going to be the mass of the salt and whatever water that we put in. We're going to have an initial and final temperature. So we'll get a delta T. Use the same heat capacity and calorimeter constant. And then we can divide again by the moles of ammonium chloride that are produced to solve for delta H. So now we have 2 delta H's that are somewhat related to our target equation, but they're not exactly. So we're not quite there yet. We need 2 more reactions. I'm going to show them to you now. The delta H values you don't calculate. You're going to be given them in your post lab, but I'm not even going to bother with numbers right now because it's not important. But these are the reactions that you'll be given in your post lab, and you'll need them, these 4 reactions, to appropriately do Hess's law and solve for this overall enthalpy of our target reaction. So 4 of them, but only the enthalpies, change in enthalpy 1 and change in enthalpy 2, you will do in the simulate, and you'll do just like the magnesium and HCl reaction. These are given in the post lab. These numbers are given in the post lab. You'll have all of these numbers, and then we'll begin our Hess's law analysis. So now we want to have solid ammonium chloride on our reactant side, and we want to have gaseous ammonia and gaseous hydrogen chloride on our product side, and nothing else. Everything else has to cancel. And so if our analysis has been done right, it all should cancel as long as we flip the right things and scale everything. So let's see, we got to have this ammonium chloride on the correct side. So we have it, but now we have 2 of this ammonium chloride aqueous on our product side. And we don't want that at all. So we're going to flip delta H1 and flip its sign. So now we have this aqueous ammonium chloride on our reactant side. We just flipped this first reaction and flipped the sign. And now we want to have our gaseous ammonia and gaseous hydrogen chloride on our product side. And right now they're on our reactant side. So we're going to flip reactions 3, and we're going to flip the sign of the delta H3, and we're going to flip reaction 4, and we're going to flip the sign of delta H4. And then if we've done all of our math correct, Hess's law says that I'm sorry. So we're going to cancel out anything that's both on the product and reactant side. So like the aqueous ammonium chloride, the aqueous hydrochloric acid, the aqueous ammonia, and then we can see that we have only on our reactant side what we're looking for, the solid ammonium chloride and the gaseous ammonia and the gaseous hydrogen chloride. And so where I was going to say is that we've done our analysis correct, then we can add up these enthalpies, the 2 that we've calculated with 1 flipped, the 2 that are in the post lab, both flipped. We can sum them up and make sure all the signs are correct. And those should add up based on Hess's law based on the fact that delta H is a state function and is path independent, that delta H overall should be the delta H of our target reaction, which would be impossible for us to do today. So just a quick look at what you're going to see in the post-lab data collection from that first calculation of the calorimeter constant. Here's where you're going to actually calculate the calorimeter constant, and so we've already seen that math. Here's the data that you're going to need on the mass of magnesium and the hydrochloric acid for part 2. And then you're very similarly, you're going to be doing the delta H of this neutralization of HCl, so the data will go in here. You'll calculate that delta H when you divide by the correct number of moles, and so you'll plug that in here, and you'll need that for the last Hess's law analysis. You'll do that last equation where you're just dissolving the solid ammonium chloride in water, so you'll have to collect all of that data, the delta T's as well. Same thing, you're going to calculate your enthalpy for that reaction, and then these are the 2 last reactions that I mentioned. These are the changes in enthalpy you can expect for every 1 mole. And so then you'll have 4 delta H's, 4 reactions, flip, 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 where you need to, cancel things out, add up the delta H's, and you should be able to get that target delta H. So let's conserve energy and begin, unless there's any further questions.